Today I'm going to go through the requirements for the motor controller that I am designing for Charly. Now, as a recap, Charly is a vintage 1990s electric scooter that was lead acid and had a pretty archaic controller in it. All of that, when I got it, was more or less stripped away. There was no lead acid batteries, no controller, and just sort of the bones of the scooter. So since then, we've retrofitted it with a 48 volt lithium ion battery. We've created a new main controller for it that has an ARM processor on it. So this is taking in the sensors like the brake sensors, the throttle sensor, controls for the horn and the lights, and it has drivers to be able to drive these headlights. We've replaced the headlights with LED headlights, which is a lot more efficient. The horn is still a TBD thing. Like right now I still have the original horn, but it doesn't have a place to live at the moment, and it may need a housing created to be strapped to the front handlebar. Not sure what's going to happen with that. The brake sensors haven't been designed yet. They may end up just being left as switches, although I'd rather not do it that way. This display itself, it has 3 7-segment LED displays on it with a 10-segment LED bar. And then there's also an OLED display, which allows me to display other information such as battery voltage, currents. It's whatever I'm going to figure out what I'm going to display at. I'm not sure yet what I'm going to put there. The main speed of the bike will be obviously displayed on the 3-digit display. So this is interfacing with that ARM processor through an I2C bus. And all the information, like I said, that was collected on the ARM, it is available on a CAN network. So the CAN network is what is going to be used to talk between the main controller and the motor controller. And then there's also going to be an interlock system with that as well, which I'll talk a little bit further on. So how do we figure out what the controller requirements are going to be? Some of that's related to, what is your battery that you're using in your system? What's the motor that you're using? What sort of desirable characteristics you want? So in my case, my upper limit on the battery is what its maximum charge voltage is, which is the 56 volts. And just for the sake of it, I just said, okay, well, we've got to be able to withstand at least surge to 63. And that was chosen more because that's typically the one of the boundary voltages for electrolytic capacitors. The second requirement I wanted was I wanted to be able to drive this both motoring and also in regen mode. So that's first and second quadrants. And a lot of the simple scooter controllers will not have that capability. It'll just strictly be motoring or not. One of the big things that's really important is because we're not dealing with lead acid or lead gel, there has to be limits placed on how much battery current you'll draw during peak power output. So in the case of my battery, it's limited to 25 amps, although I've seen documentation saying 30. I'm not going to push it. I'm going to limit it to 25. So that means that once you've hit that 25 amps, you're now in a constant power mode. For regen, it really is limited to 2 amps. That's the charge current returning back to the battery, and I think that is the BMS limited. There's probably something related to the battery itself as to how much current you can actually push back into it. So that could be battery limited as well. I don't have, or I do have the cell information, although I'm not sure that it is the cell that's in there. I haven't taken the pack apart in a while, so I can't remember what was there. Some of the other things we want with this motor controller is that we want to be able to measure the bridge temperature. So bridge temperature is what the MOSFET temperature is. And we also want to be looking at what the voltage and current inputs are to this controller. We want to know what the output voltage is, so the motor voltage, and what the current is going out to the motor, as well as motor temperature. Other things that we want, obviously, as I said before, we want to use the CAN bus to be moving the information back and forth. So all the set points for the torque or speed, depends on how this is written up, have to come from the ARM processor on the main controller board. So that's all done through the CAN. Now, if you're sending CAN messages down about every 2 milliseconds or so, that's loads of time to get a smooth response. Some of the other things that we need is on this controller, we need to have some low side contactor drivers, or low side drivers, period. And the reason I'm looking for this is that there's an interlock put onto the main contactor which separates the battery and the motor, or the motor controller, I should say. So if we have a fault in either the main controller or the motor controller, either one of them can terminate the or shut down the main contactor and remove the power from the bridge. And that's not a typical thing you see in the cheap e-bikes. That's another thing we need is we have to be able to have a separate low voltage supply input line. So that's the battery voltage coming into a DC-DC switcher, which is generating the local logic voltage supplies. Additionally, we need the controller to be able to output the current that will give maximum output mechanical power. So that kind of gives you an upper limit as to how big your controller needs to be, or what sort of current rating your motor controller needs to have. And I'm arbitrarily choosing that point. I mean, I could make this into a really overdone motor controller. It's just cost, right? So when you're doing it for yourself, you're rolling your own, it doesn't matter so much about how many MOSFETs you're going to put into the bridge. If you're manufacturing this for sale, obviously you want to minimize the amount of MOSFETs you put in, and maximize the output power that you can put out of it. The last thing that I'm looking for is I need to have a counter input that can take the pulse from my encoder that's on the motor. Now I've created this and installed it because I want a lot tighter feedback on speed than what I would get from the single pulse per revolution that you get from the front wheel. And my hope is that this is good enough to be able to wrap a wheelie popper, or should I say anti-wheelie popper control into the throttle, because Charly, it's small, compact, and deadly. It has such a bad center of gravity that if you have poor control over the torque to the motor, you'll end up on your butt. And probably you don't want to be doing this at speed. So that's kind of where we're at with what the requirements look like. Now, if you look at the Charly motor, this is made by Bosch. This motor is no longer manufactured. However, it is a nice little motor. Very, very powerful for its size. And it is a continuous duty motor, so the ratings that they put in there, so the 40 amps, 750 watts, in theory should be their continuous max power for whatever temperature the windings are going to get to. If you put in additional cooling, you can probably boost that nominal rating, but practically speaking, it's not necessary. So the other thing that was on the data sheet is the motor characteristic curves. And from this, you can find out all the critical information you need for sort of setting the limits. So now, when I look at the max power, shaft power that is, they're listing it at about 1200 watts roughly. And at that point, that current level for that 1200 watts is about 94 amps. So that's 94 amps going into the motor. So that's what I would look at as a temporary overload condition for the bridge. You couldn't operate up in that range without overheating the motor over time. You notice that the ratings that they give you, the nominal ratings, the 750 watts, corresponds to the 40 amps on the current versus torque curve, and also the nominal torque of 2.2. So all that's how you would determine where you want to be on the curves. You can then get the other parameters very easily. An interesting thing is the stall torque. So that's the point at which the motor is locked, a lock rotor, and that's the maximum current that will go into it. So from that you can actually calculate out a rough resistance, which is going to be the brushes plus the windings. So I got about 135 milliohms. So that's just, obviously you're not going to operate in that region of the motor current torque. However, it's just when you're putting a model together, there's various things you can do for speed control, which require you to know what that resistance is, and also what the back EMF constant is. But I won't bother going into that right now. So my limits then will be 100 amps for the sake of it on the controller, and then we'll add some margin into that, so 125 amps, so about 25% additional margin on the bridge. So you're not actually going to be able to operate up there, because what will end up happening is you're going to reach a battery limit very quickly. So when you start getting up in this area, your battery current is going to be quite high. So you likely can't actually even reach this, but I haven't done the calculations yet to see how close we can get to max power output. I think it's close, but again, I need to do the calculations. So now that we got kind of the limits kind of set for what we need for the controller, and we have our requirements in place, I've kind of sketched together a block diagram of what I'm going to try and build. So what we have then is a half bridge power PWM bridge. The wave shapers are just RCs that allow you to, well, actually there'll be more R's and a D, which will allow you to kind of do an asymmetrical wave shape. So when you're trying to turn the MOSFET on, you can adjust the timing to be different than what you're turning it off. And when I get to the point where I start doing tuning of MOSFETs, I'll explain why that's important. But it has to do with the Miller capacitance and the charge induced into the or injected into the gates, and also the voltage overshoots. And again, I'll go into that later. For my sensor feedback on the motor, I'm looking at a plus or minus 150 amp sensor. There's no way I'm going to be putting 150 amps back into the battery. I'm going to be looking at 2 amps at most, but I need to be able to measure bidirectional. So that's current coming back through the bridge, and then we also have a Hall sensor on the battery feed. So this is better. This is a plus or minus 30 amp sensor, so a little bit better resolution, not hugely. 2 amps is still limited to what you're going to go in, but since the battery is limited to 25 amps output, this will fall in quite nicely in the range. The processor I'm looking at is the UCD 3138064. So that is a TI dedicated power controller chip. It's not intended for motor control. This is intended for AC/DC power supplies, but it's a very flexible chip. All the current loops or the control loops are actually run in hardware. And so you're not running into the problems of trying to make your interrupts very short to be able to do your current loops. And I think, like, because it isn't designed for this, I'm not 100% sure that it will work the way I want it to work. I know this thing will work fine in a motoring situation, but when we start stacking loops, so you want to be stacking the battery loop with the motor control loop, so that when one limit is reached, then it limits the full current output of the controller. And that's to make sure that we're within the safe current output or input of the battery and safe current output or current input of the motor. Obviously there's the basics, like, so this chip does not have CAN native, so we need to add a CAN controller onto it. DC-DC power supplies that convert the 56 down to something useful, so we need 12, 5, and 3.3. Now the ratings on the 12 is because we're actually going to be driving the rear LED brake light, and it'll need to be able to probably drive some other loads that I haven't determined yet. We also need contactor, low-side contactor drivers, so that will be what controls the tail light to turn on and off, and it'll also be the sync side of the main contactor circuit. So this allows me then to, if I run into a fault condition, to shut off the main contactor, and then that disconnects the battery. Additionally, we're looking at putting a hardware watchdog on this in addition to the internal watchdog that exists. And this is done just to give us one more level of protection. And I'm not sure when I'm going to interlock it on, because we need CAN communications to be regular. It might be based on the internal or the interrupt status line coming off of the CAN controller. So if it's not kicking the hardware watchdog enough, then it'll just automatically disable the bridge. So that can then make sure that we don't have a dead controller necessarily that can't control the contactor and shut it down if necessary. Additionally, we got the thermistor for the motor, so that'll be a wired thermistor that gets bolted to the case of the motor. And then we have the thermistor for the bridge, and that'll be dislocated probably on the heatsink of the whatever the TO220 MOSFETs are mounted to. So the MOSFETs are going to be mounted to the donor aluminum extrusion that came off of the old Robotech controller. And I don't expect problems with reusing that. I'm going to trim it down to be the size I need for this, because this is not going to be a very large controller per se. My guess is it's probably 2 FETs for the top switch and 2 FETs for the bottom. So that doesn't really require a lot of heatsink space. It does, however, if it's switching inefficiently. And that is going to be dealt with during the tuning process, and hopefully, and also the layout. So hopefully we'll have a clean layout that keeps the loop areas small, so that we can keep the switching, like the turn on turn off times, quick. So that's it for now, and in the near future I will do an update on where we're at with the main controller.